is also conserved, where energy we define as at least the mechanical energy in our case, where it's just a sum of the kinetic as well as the potential energies. Now there's a type of interaction that actually combines both of these together, and this is the final type of collision, what is called the elastic collision. A collision is said to be elastic if, or is a collision in which mechanical energy is conserved. Collision in which mechanical energy is conserved. So recall, collisions also conserve momentum as well. So recall, collisions also conserve momentum. So an elastic collision conserves both momentum and mechanical energy. So to come up with some expressions to get a full understanding of what's going on, let's consider a specific scenario. Let's say ball number 1, stationary. Ball number 1 is moving. And ball number 2 is stationary. Well, from here, we can apply conservation of momentum to our scenario because it is a collision. Conservation of momentum would look something like the following. M1, and let's say and in the x direction, and let's just consider one direction for simplicity. Conservation of momentum will tell us m1 v1f in the x direction plus m2 v2f in the x direction. That's just the momentum of the first object plus the momentum of the second. This is going to equal the initial momentums, which is m1 v1 naught x plus m2 v2 naught x. Now in this scenario, what can we immediately simplify? Huh? No, we don't know if the masses are the same.
The initial velocity of ball 2 is 0.
Yes. Ball 2 is stationary, so the initial, that guy is equal to 0. But that's only conservation of momentum. Elastic collisions have their energy conserved as well, so we can apply conservation of energy where we only have the kinetic energy. Let's say they're on the same plane, it's only in the x direction. So we have 1/2 m1 v1 f squared plus 1/2 m2 v2 f squared. This is equal to 1/2 m1 v1 naught squared plus 1/2 m2 v2 naught squared. And as before, the initial speed of object 1 is 0, so we can reduce L to that. So let's say the things that we know, essentially this scenario, ball 1 is moving and ball 2 is stationary. They are going to collide. So you can think of it as a set of billiard table. You hit the cue ball, and the cue ball hits a stationary ball, and then that's kind of the interaction that we're looking at here. So let's say we know the masses M1 and M2. And we also know the initial speeds. The initial speeds, not the final speeds. But as an aside, V1 naught is also equal to, because it's only in the x direction, we have these relationships. V1 naught is actually equal to V1 naught x. Likewise, V2 naught is equal to V2 naught x, as well as their finals. V1f is equal to V1 fx. V2f is also equal to V2 fx. Now for a collision, often what you want to know is the velocity of the final states, of the final scenario. What we want is V2fx and V1fx. That's what we are looking for. So we have two equations. And if you catalog every single parameter on here, you'll notice that we know everything except just these two. So here we have two unknowns, but we have also have two equations. Meaning we can actually solve for what the velocities are. Simply by doing the solving it as a system of equations. You find one of the parameters and then plug it back in to the other equation, so on and so forth.
Thank you.
Now, I'm not going to do that here. The proof is going to be for the problem set. Proof for P set. But I'm just going to give you the final expression here, where V1fx is going to be M1 minus M2 over M1 plus M2 times V1x. How did I write this? V1, yeah, V1 naught x. The second object is going to be 2M1 over M1 plus M2 times V1 naught x. This is true for elastic collisions. For elastic collisions only. Because we derived this expression based on the assumption that conservation of energy is true. Now, another assumption that we made, or another assumption that went into this derivation, was the fact that one of the objects was stationary. Well, what if we alleviate that? Because in not all scenarios is an object going to be stationary. So the question we have remaining is, what if both objects are moving? Answer: we can still use this. You can still use these two expressions as long as you make one modification. So can use same relationship as long as you do one thing. What we're going to be doing is use relative motion. You can always choose a reference point that is moving, as long as it's just moving at constant velocity. If it's accelerating, then you can't, because we are no longer in the inertial reference frame. However, if something is moving with a constant speed, you can. we are going to use that. Use relative motion, let's say with respect to object 2. Meaning V1, we'll say new, is going to be V1 old minus V2 old. So we just cared about the relative speed one has with respect to object number 2. We're going to do that with the second object as well. And all we are doing to use this relative motion is to subtract your speed from object number 2's old speed, which is going to be V2 old minus V2 old. So what is the new speed of object number 2? Yeah, it is going to be 0. And you see, now we have effectively a stationary object number 2, which meets the conditions, and therefore we can use these two expressions for our final solution. So here, one is stationary, but one is moving with a new speed, which is the difference of their old speeds. All right, so that ends the collision section. But before we move on, one of the things that I wanted to do, or move on to the next major section, is so far we talked about energy, but we didn't make a connection to force. So far we talked about forces, but we didn't, and then we talked about things like momentum and energy, but we didn't actually connect both of these things together. And to do that, we are going to talk about this concept of work. Concept of work. Work in a loose sense is just ability, well, we'll just call it force times distance. Work is also a form of energy, meaning it has units of joules. So, work is going to be force dotted with a, we'll call it distance, lowercase d. Which is equal to FD times cosine of theta. And so this is the relationship of force to the energy concept. Work is a form of energy. So when you apply a force and you're actually moving something, you're actually giving something energy because you are doing work onto that object. That is work. I also have to discuss what is called power. Power. Now, to give you guys an introduction on what power is, people talk a lot about energy. Right? You need energy to do pretty much anything, and you're also, who lives in an apartment or lived in an apartment so on and so forth. You know that you not just pay for your rent, but what else do you pay for? Right, cell phone bills, right? Utility, what else?
Water.
Huh? Yeah, water.
Gas.
But you have an electric bill, right? You have an electric bill. Ultimately, that is electric energy that you are purchasing. Electric energy. Now, what if I were to tell you that there is a device that can make free energy? That will mean every single electric company, I can get them out of business, and I can immediately become a billionaire, probably the richest person in the world. There is such a device, by the way, but nobody's using it. Even though it can make infinite energy for pretty much free. Why is nobody using it? Huh? No, it's not us. Human labor? No. Oh, I didn't think of that. That's called slavery, Dr. Kim. Yeah, right. No, it's not free. You have to be fed, right? It's kind of expensive. It's because, just because you have infinite energy doesn't mean you're supplying it fast enough. I can give you infinite money over a period of infinite time. Is that going to make you rich? The answer is no. You're only going to be rich if I give you a lot of money very quickly, right? If I give you a lot of money very quickly, then you're going to be very rich. However, if I give you infinite money, but I give it so slow, no, then it's pretty much I'm not giving you anything at all. That is what the difference between energy and power is. Energy, just because you're able to make energy, doesn't mean you're giving it enough to actually run anything. That's why some appliances, if you just plug it into the wall here, it's not going to work, because what the wall supplies is not enough to work these industrial-sized equipment. That's why if you go to, like these hardware shops and stuff, they actually need not this typical plugins. They have a specialized plugin because their machinery actually requires a lot more energy very quickly. That is a concept of power. Power is energy per time. That is what power is, at least in the scientific sense. Actually, so we'll say E over delta T. There you go. The energy that is given per time. So the equipment that I mentioned, people are looking into it, but no one has succeeded because, yes, even though it pretty much makes free energy, it can't power anything. It gives it so slowly that it can't even charge your phone. Like, that's how weak it is. All right, so these are kind of more relevant for Physics 2, but it is typically introduced in this section, so I'm doing it. But it's not, I don't think there's really a lot of meaningful questions that can be asked, at least in this semester. So I just want to introduce it, and we'll come back to this next semester. So some conceptual problems I'll definitely ask, but not too much aside from that. And this completes the three main branches that I laid out for you guys in the first lecture. Remember the kinematics section, which is describing motion. The second one is dynamics, what causes motion. The third branch was these conservation laws, that's conservation of momentum and conservation of energy. We finished all three. Therefore, what's remaining, right? Now, if you guys also remember from the first lecture, we only did those in the context of translational motion. After translational motion, I told you guys rotation is going to be very, very difficult. And now that we finished everything with translational motion, we now have a framework on how to apply it into different types of motions. So that's where we are headed next. We are doing what I would consider the most difficult section of this semester, rotating bodies. That's where we are going next. So rotating bodies. So pretty much everything that we discussed up to this point, we are going to revisit pretty much all of it. This time, not when a body is translating, but when an object is rotating, yes.
So I just want to make sure, since work is a type of energy, could you say that power is work over delta T, or?
Yes. So work can supply some amount of power,
Okay.
but it's not always. But power is a much more generic term. Can it be? It can be work over time, yes. But it's not only work over time, because there's other forms of energy.
Right.
Yeah.
Okay, got it.
So rotating body. So let's recall what rotation even is. Recall that there are 3 types of rigid body motion. The first one is when an object just begins at a certain location and then moves or translates to a different location. This is translation. Then that second one, instead of it moving to a new location, it just moves to a new orientation by pointing in a different direction, and this would be an example of rotation. And then the last one is what is called vibration, when an object is just oscillating back and forth. And pretty much everything moves in a combination of these 3. We completely exhausted, at least not to an infinite degree, but all the major categories of translation. That's what we accomplished. We can still do that with rotation. With vibration, just because of the nature that it's not actually moving a whole lot, there's really not too much to talk about vibration, so we're not actually going to delve deeper into that. We'll get a little bit into it in second semester, but not too much. But we will be essentially spending the next 2 weeks talking about rotation. This, I believe, is the hardest section because it requires you to have really a transformation in thought. You really need to change your perspective on how you view things. But we'll get to that when we get there. What I'm going to begin with is actually giving you the final results so that you can kind of see it beforehand, because I want to convince you, mathematically, we're not learning anything like brand new or brand spectacular. Like, we're using the same idea that we have done before. So essentially, let's start with a summary table so that you will be convinced of what I just said. I'm going to give you what it was in the translational motion. Then I'm going to give you what it is in rotation. In our translation section, we discussed things like mass. We discussed force. We discussed velocity, acceleration, and momentum. In translational motion, we called mass, what symbol did we give it? Yeah, lowercase m. What about force? Capital F, and we have to remember that it is a vector. Velocity, we gave it v. Acceleration, we gave it a. Who remembers momentum? Yes, lowercase p. For rotation, at least in terms of the math, all we're doing is rewriting this with a different notation. For mass, we're going to call it I. This is inertia. There is rotational force. We don't call it force, we call it torque. It's T-O-R-Q-U-E, torque. And we give it the notation Greek letter tau. And it is a vector. For velocity and acceleration, we are borrowing from circular motion, which is omega and alpha. For momentum, we are going to be using L. The reason why I'm giving you this is we have a few additional rows as our entries. Put a dotted line here. We also looked at what is called Newton's second law. We also looked at conservation of energy, or let's call it kinetic energy. And we looked at the various conservation laws of conservation of momentum. Conservation of Newton's second law was what? Remember, this should be like the back of your hand. Huh? Was it? Yeah, F equals ma. F net is equal to mass times the acceleration. The reason why I gave you this table up here is whatever you see here in translation, if you see an F, just replace it with whatever's on that side. If you see a mass, replace it with whatever's on that side. If you see an acceleration, you replace it with whatever's on that side. So there's a Newton's second law for rotation, which will look like what? Instead of F, you're going to have a what? Yes, tau, so it'll be tau net is going to be equal to, instead of mass, what do you have? Huh?
Inertia.
You have inertia I. And what comes in? I alpha. This is correct. Newton's second law for rotation is this. Just like how the net force gets an object to move in a translation, the net torque is going to get the object to rotate. Right? It'll get it to rotate. Kinetic energy, which we call it K, we'll call it K sub T for translation. This was equal to 1/2 mv squared. In rotation, we're going to call it K, let's call it ROT for rotation. This is going to be what? Once again, whenever you see an M, replace it with whatever's on the other side. Whenever you see a V, place it on the other side. So what is it? 1/2 I omega squared is correct. Oh, I forgot one thing here. There's supposed to be momentum. Momentum P was equal to mv. So then the angular momentum is going to be equal to what? What is it? Yeah, I omega. And we have conservation of momentum as well as conservation of energy. Conservation of momentum tells us that the total momentum final is going to be equal to total momentum initial. In angular momentum, we have angular momentum being conserved. L naught is equal to L final. So it's not only linear momentum that's conserved, but angular momentum that's conserved. What about conservation of energy? Well, we have translational plus the potential. Well, let's also put spring in there because we did. We'll say this is conserved. With rotational energy in mind, we actually have KT plus, there's that kinetic rotational energy now, plus UG plus USP is conserved. So when you're rotating, there is an additional energy term. Now, this is the reason why, who remembers lab number 3? Who remembers lab number 2 and 3? They're kind of a pair. Maddie, remember? What was the goal?
For lab number 2.
Yeah, 2 and 3.
It was 2 the one where it was dropped on the board sideways, or is that the?
That's number 3.
That was number 3. Okay.
But what was the goal? That's correct. But what was the goal?
To compare the actual value of G with the value that you were calculating based
Yes.
on
Yes, get the gravitational constant G. We did it in 2 ways, right? In lab number 2, we did it doing free fall. Lab number 3 was we dropped it down an inclined plane. In those labs, which one gave a better estimation for G? Right, I think pretty much everyone got it correct. Free fall was closer to 9.8. Inclined plane was closer to like 5 or 6. Do you guys all remember this? Now, you guys know why. So on Thursday, you're actually going to do the lab correctly. The reason why is, what object did we use when we were doing the inclined plane? We used a what?
Do these pieces like this slab?
Yeah, but what did we drop? Or what did we?
A ball.
Yeah, a tennis ball. The tennis ball didn't just slide down, right? What happened to the tennis ball? It started rolling. Instead of all the energy just going down to the speed, some of that energy was converted to making the ball roll. That is why your G estimation for the inclined plane was so wrong. Okay, yeah, so yeah, essentially I lied to you guys at the very beginning. But ultimately, it's so that you guys actually understand how important it is to learn new concepts. So actually this Thursday, you're going to redo the lab, except you're going to do it correctly. You're actually going to be doing it considering this, and you're going to get a much, much better estimation for G coming from the inclined plane, because you now know why, or you at least know what went wrong in the first place. So the lab this week should be super duper simple because you pretty much did it once. You're repeating that same exact procedure with, you're collecting one additional piece of data. And that data is for you to just see how quickly the ball is rolling when it's at the bottom. Once you consider all those things, you're going to get a really, really good value for G. Free fall is still going to be better though, but that kind of comes with it. All right, so that's as an aside. But one of the reasons why rotation is actually very difficult is because you actually have to do a few things before you can even do the calculations. For example, in translation, once you're given mass, you just use it, right? For inertia, that is not the case. For inertia, you need to know what the mass is as well as some information about the general shape. This is actually equal to, I'm just going to give it as an equation. Mass is the sum of mass times the radius squared. So you're not just going to be given inertia. you're still going to be given mass, but it's your job to calculate what the inertia is. So you need to do some pre-work, if you want to call it that. Also, force to torque, you actually have to do an additional calculation as well. So I'm sure you guys know, or maybe you know, let's say who's ever tried to open a really heavy door? Yeah, for you guys, you look like sissies in front of your girls you're trying to impress. I mean, that's not very good, right? Sam apparently knows what I'm talking about. How do you get the door to open on a surprisingly heavy door? You could either push harder, that's obviously true, or just change where you're pushing. Right? Instead of pushing it closer to the axis point, you can push further away. So with the same force, you can actually have a different amount of torque, because torque actually depends on not just the force, but how far away you're pushing. So the equation looks like this. It is R cross F. This is actually what is called the cross product. It is not a multiplication. It is a form of multiplication, but for vectors. Likewise, for angular momentum, this is R cross P. Now, before we can even do rotation, we need to go over what a cross product is. Because this is important when you're trying to do torque and momentum calculations. And so get on your thinking caps. This is one of the main reasons why I do believe rotation section is going to be quite difficult. So let's go over what this cross product is. This is typically taught in Calc 3 or Calc 4. However, it's just a small portion of it, so we are going to be going over that here. Instead of math, it's more of a notation kind of a thing. So you're not actually learning Calc 3 or 4. You're just going over some of the notations that they actually are using. And the calc-based class got so confused after this, I just decided to call it a day. As likely that will be for you guys too. So let's go over this concept of a cross product. A cross B will equal, let's say, C. Two vectors are going to be crossed to form another vector. Because the product is a vector, we need to go over the magnitude as well as the direction. The magnitude is given by this. A, the magnitude of A times the magnitude of B times the sine of the angle in between them. So it's AB sine of theta. But for vectors, you not only have the magnitude, you also have the direction. So we need to go over that as well. The direction is perpendicular to both A and B. And you might be thinking, wow, that's kind of confusing. So let's draw a simple sketch. So let's say this is vector A. And this is vector B. there will always, it doesn't matter what two vectors you use, there will always be a plane that you can draw that contains both of these vectors. So we can draw a plane that contains both of these vectors. No exceptions. Any two vectors that has the same origin, you can draw a plane on them. The reason why we want to draw this plane is this statement is perpendicular to both A and B. Is simply saying our vector C is going to be perpendicular to this plane. That's pretty much all that's saying. So A cross B is going to be a vector C that's going up out of the page. So this is just what the cross product is. Don't ask me why, at least right now, just this is, understand this is the mathematical notation of the cross product. But right now, there should be a glaring question. You guys see it? If you don't have a question, you're wrong. You should have a question. Can you spot what that question is?
Why is it going out of the plane upwards instead of to the right of both A and B?
Okay, you were so close. Your first part was right. I thought it was right, but no. So, why is it not going where?
Like just to the right of
To the
A,
right?
Yeah, an angle. Yeah, like
Incorrect.
just in between the two angles.
Or in between the two? Well, it would be in between the two if you're adding. It would be this way if you're like subtracting.
Right.
But multiplication is not adding or subtracting, so
Oh,
yeah. So this statement is still in play, that it's perpendicular, that's just what it is. But man, you had 50%. You had 50% of your statement was 100% correct.
What?
Which is why instead of the vector going up,